Consider 3 points A, B and C in space. If points A, B and C are collinear, then an infinite number of intersecting planes can pass through them. Thus, we cannot determine a unique plane in this case. However, a unique plane can be determined if it passes through 3 non-collinear points. Let us derive the vector form of the equation of a plane passing through 3 non-collinear points A, B and C. Let vectors A, B and C be the position vectors of points A, B and C respectively. Since the plane passes through points A, B and C, they are coplanar. Thus vectors AB and AC lie in the same plane. Thus, the cross product of vectors AB and AC is equal to vector n, which is perpendicular to the plane containing vectors AB and AC. Let this be equation 1. Let P be another point on the plane having position vector r. We already know that the equation of a plane passing through a given point with position vector A and normal to a given vector n is given by equation 2. Substituting the value of vector n from equation 1 in equation 2, we get equation 3. Applying the triangle law of vector addition to triangle OAB and rearranging the result, we get equation 4. Similarly, applying the triangle law of vector addition to triangle OAC and rearranging the result, we get equation 5. Substituting the values of vectors AB and AC from equations 4 and 5 in equation 3, we get equation 6, which is the vector equation of a plane passing through 3 non-collinear points A, B and C. Now, let us derive the Cartesian form of the equation of a plane passing through 3 non-collinear points. Let the coordinates of points A, B and C be as shown. Consider another point P on the given plane having the coordinates x, y and z. If the position vectors of points A and P are vector A and vector r respectively, then we can write vector AP as shown. Similarly, we can write vector AB and vector AC as shown. Substituting the previous values in the vector equation of the plane passing through non-collinear points A, B and C, we get equation 7 as shown. Converting equation 7 into a determinant, as shown here, we get the Cartesian form of the equation of a plane passing through 3 non-collinear points A, B and C with the given coordinates. Consider 2 planes, pi1 and pi2, intersecting at a line, as shown. Now, consider another plane, pi3, passing through the line of intersection of planes pi1 and pi2. We will first derive the vector form of the equation of plane pi3 passing through the intersection of 2 given planes pi1 and pi2. Let the normal form of the equation of plane pi1 be given by equation 1. Here, vector r is the position vector of a point on the plane. Vector n1 is the unit vector along the normal to plane pi1. and d1 is the distance of plane pi1 from the origin. Also, let the normal form of the equation of plane pi2 be given by equation 2. Let A be any arbitrary point with position vector A on the line of intersection of planes pi1 and pi2. Since point A lies on both the planes pi1 and pi2, its position vector must satisfy both equations 1 and 2. This gives us equations 3 and 4. Combining the equations of planes pi1 and pi2 for point A, we get equation 5. The line of intersection of planes pi1 and pi2 contains an infinite number of points. For any such point with position vector r that satisfies the equations of both planes pi1 and pi2, we can rewrite equation 5 as equation 6. An infinite number of planes can pass through the line of intersection of planes pi1 and pi2 for different values of the scalar lambda. Now, we will derive the Cartesian form of the equation of plane pi3 passing through the intersection of planes pi1 and pi2. Let the values of position vector r and normal vectors n1 and n2 for planes pi1 and pi2 be as shown here. Substituting the values of position vector r and normal vectors n1 and n2 in equation 6 and simplifying, we get the Cartesian form of the equation of a plane passing through the intersection of two planes.